Great. Now that my mic is on, I can get started. Thank you for the introduction. So my name is Sanne Bloot. I am a PhD student at Astron and the University of Groningen, and I am a radio astronomer, but I work on stars, which can be confusing, but at least we've had a couple of radio talks this week, so I'm not quite the first one to talk about this. What I'll be talking about today is how we can use radio observations to constrain what the stellar winds of, in particular, M dwarfs are like. Now, to start with introducing that concept a little bit, I am a cool stars. This probably doesn't need too much introduction, but stellar winds are very important for things like stellar evolution, but also, as we've heard about this week, for interactions between a planet and a star, where the stellar wind can determine whether that interaction can happen or not. And as we will hear about later as well, stellar winds can have a very strong impact on how planets evolve in that situation as well. So I'm specifically interested in low mass stars, and for low mass stars, their winds are extremely tenuous and very difficult to measure because their winds are also very low mass. So the way that this has been traditionally measured mostly has been using atmospheric absorption, the Lyman alpha lines. So that is, let's see if the pointer works. Yes, it does. That would be, for example, something like this, where we have absorption from, this is one of the absorption lines in the spectrum. We have the absorption from the ISM. And if we model that very carefully, you can see that there's a little bit of excess absorption right here. And that excess absorption is thought to be caused by the edge of the astrosphere, where there's another extra layer of absorption happening. Now, that is just a little bit of excess absorption. And this model needs to be known very, very carefully. Like, you need to be very, very sure what that bit looks like before you can start making any claims about how much excess absorption you have and how that relates to your stellar wind. So this work has been mostly done by Wood et al. And this work is very strongly dependent on understanding what your interstellar medium looks like and fully understanding what the impacts of your model are on the results that you're getting out. Because it is strongly dependent on the conditions of the ISM and us knowing about those, this method is really only applicable within, let's say, the local bubble. It can be applied outside of that as well. But the further you get away from the sun, the more difficult it gets to properly interpret the measurements that come out of this. So what I'm talking about today is how to measure these stellar winds independent from these types of measurements, and instead using radio emission. So I'm not the very first person to have had this idea. If this wants to go to the next slide, would be nice. But the basic concept of this idea is when we detect radio emission from a star, we know that it has not been absorbed. It has escaped from the stellar wind and reached our detector. So I've put a little star here, given it a stellar wind. Now, if we give it a region of radio emission, in blue right here, and we assume that this radio emission has to escape all the way from the surface out to our detector, and that gives us an upper limit on the amount of density this radiation has encountered between this point and that point. So that will give us not quite a measurement of the mass loss rate, but it will give us an upper limit on the density between there and there. This has been done by Lim and White, who assumed that their radio source was on the surface because that was the information they had to work with. But what I'm presenting now is we have slightly better information now. So if I now give that star, yes, there we go. If I give this star a dipole magnetic field, and I say we've detected emission through the electron cyclotron maser instability from it. Now, this emission mechanism has actually been mentioned in a talk earlier in this session, which I'm very grateful. This emission is produced at a frequency that directly and only depends on the magnetic field strength in the region. So we can use it to measure magnetic field strengths of objects. But if we know what the magnetic field structure of a star looks like, for example, this lovely dipole, then that number will tell us where in this dipole field this emission can be produced. So what that will actually give us, it will give us a surface in the field where the value is exactly what we need it to be. To be slightly careful with our estimations here, we assume that the emission is as close to us as it can be. Then at that point in the wind where the field strength matches the observed frequency of the emission. And that now gives us a somewhat established source location. Now when we take that source and we trace that emission outwards again through the stellar wind to our detector, which in this case is LOFAR, the low frequency array, then that gives us a constraint again on the density between this point and that point, but now with more accuracy and slightly better understanding of where the source actually is. So when we apply this to a hypothetical star to see what this method looks like, what we get is something like this. So here I've put the strength of the dipole. So just to put that in context with this plot, if the dipole field here is very strong, but you know that you've measured this at a frequency that corresponds to about 20 Gauss, that means your source can be very far away from the surface. It might be all the way over here. Whereas if the magnetic field strength of your star is measured to be only 20 Gauss, you know it has to be on the surface. Now, the field strength has been measured to be even less than that. I'm talking about the large-scale fielder, large-scale dipole. The large-scale dipole is known to be maybe only 1 Gauss, like the sun. And that means that this emission now needs to be produced in local variations, small coronal loops on the surface. So for those cases, we assume the emission comes from the surface as well. Now, going back to the plot that I was showing here, as a function of dipole field strength, this is a dipole of the star, we can plot the upper limit on the mass loss rate in solar units here, which gives us for different temperatures, different values. Now, I'll start with one just to conceptually explain that. We start here with a very small, very weak dipole. The emission is on the surface, and as we move to higher dipole field strengths, the emission can now move off the surface, and we get a higher upper limit as our source location can be further out into the wind, so the emission has to cross less material to get to our detector. Now, the other factor in this plot is the temperature of the wind. So a wind that is very cold is very opaque to radio emission and will absorb it very easily, whereas a wind that is very hot will do so less easily. So what we can see is that at, for example, using 10 megakelvin as a temperature for the wind, our upper limits are relatively high. Whereas if we know that our star is cold at only 2 megakelvins, our upper limits get quite a lot lower. Now, this has all been applied to a hypothetical star, but we can apply this to real detections as well. So for those detections, what I will be using is LOFAR detected M-dwarfs, where we are relatively sure that this emission is actually driven through the ECMI process. Now, taking that results in a sample of about 19 M-dwarfs, which when I apply this method to, let's see if this will go, looks roughly like this. So here are all the black points of previous measurements and upper limits on the mass loss rate. Most of these has been determined through the atmospheric absorption method. That unfortunately does not quite result in clear error bars, so there are no error bars in this plot, but that's simply the value that comes out of the model. Now, on top of that, we have the LOFAR detected stars. So there's two colors in this plot that are relevant here. One is we have these little red points, these red upper limits. These are the stars for which we have a ZDI map, so we have a measurement of the large-scale dipole. We know exactly what the field looks like. To be specific, these are GJ-LEM 51, AD Leo, and WX Juma up there. For the other stars, we don't know what their magnetic fields look like. If anyone would like some more targets to do ZDI on, please come talk to me. I would love to know the magnetic fields of these. For now, we don't know them. So what we have done is we've estimated the magnetic field strengths of these stars based on the sample of M-dwarfs that have been detected, and use that to extrapolate a value for the magnetic field that is either roughly average for that class of star, or one that is roughly the upper limit on what the magnetic field could be for that type of star. So in the plot, this corresponds to the, let's say, pessimistic value for the magnetic field strength. This is the very large magnetic field strength, the largest this star could have. That gets you a very high upper limit because your source can be very far away. But then if we take the average magnetic field strength for a star of that type, our points move all the way down to here, where we get the, what I would say, realistic estimate for the mass loss rate for this star. However, we don't know what these magnetic fields are. That's why I'm plotting them as a range. This upper limit is probably somewhere in between these 2 points, but I really need a measurement of the large-scale field to know for sure. Even without knowing that for sure, taking just these blue values, the upper limits that we are finding are starting to get very close to the actual measurements, especially up at the high activity levels or the very high X-ray fluxes, where we can still measure the mass loss rate. Even the method itself is completely fine across this entire range. So if we can start filling in this a little bit more, we can start seeing what the mass loss rate really is doing up here. Now, the other advantage of this method is that this doesn't depend on distance. All I need is a detection of radio emission. As soon as you get me a detection of radio emission that is known to be ECMI, I can get you a point on this plot. Distance does not matter. Now, practically for this sample, we are limited to 50 parsecs because that's the furthest star we've detected so far with LOFAR. But as we're continuing with the surveys, we're expecting this to increase. We're expecting to detect many more stars and eventually fill out this entire plot. Now, this plot is the mass loss per unit surface area, which these are all M-dwarfs. So all of these values are now being boosted up a little bit compared to other stars. So just to show what that looks like, I've also made this plot with just the X-ray luminosity. So if it's a function of X-ray luminosity and a function of the mass loss rate in just number of solar masses lost per year now. what we see is that we have our points, they're all getting pretty close to the actual measured values. For the cold stars, they're still quite high up there, but for the stars with a very hot wind, they're getting very close to the already measured values. Now, one thing that you can see in this is that we have a trend with external luminosity. That trend is caused by the fact that we determine our temperatures from the external luminosity. So that is unfortunately instrumental. But with more data points, we can start seeing if this trend is actually something that is real. Now, one thing that we have assumed for these winds is that the wind is isothermal, which is not the case in the sun. But unfortunately, we don't quite know what winds around other stars look like yet. If we take a more realistic structure, like the temperature structure of the solar wind, all of these points will be pushed down by quite a lot, in fact, almost an order of magnitude each. Unfortunately, that is something that we don't quite have measured yet. We don't know what the structure looks like. So for now, this is the safe assumption. But with improved modeling of what the temperature structure of these winds look like, we can push all of these points down by quite a lot. Then I have one more bonus plot here, which is these stars a function of rotation period. We don't quite have the rotation periods for many of these, but for the ones where we do have them, we can see that all of these upper limits are getting pretty close to the regime where we have the full measurements as well. So that brings me to, oh, this is the previous version of my slide. That brings me to my summary slide, which is that if you can give me a radio measurement of your star, specifically with ECMI, I can get you a mass loss rate. If you can get me one that is a very low frequencies, I can actually get you a good constraint on the mass loss rate. Now, ideally, I would like to combine that with a magnetic field strength measurement. So if you have a magnetic field strength measurement of that, it can get a much better constraint. Finally, if we can combine this with more detailed temperature structure models for specifically M-dwarf winds, we can push these upper limits down even more. And that was the end of it. I had another conclusion on the slide, but this is apparently the previous version, so this is what we'll have to deal with. Radio detection is the most important, but if you can get me a magnetic field and a temperature as well, then we can get a very good upper limit on the mass loss rate. Thank you.
Moira Jordan from St. Andrews, great talk. I just wanted to ask how you calculate your mass loss rates, because the mass loss requires that you know the density and the velocity. So did you assume something about the velocity?
Yes, thank you. So the question was to calculate a mass loss rate, you need both the density but also the velocity of the wind. And how did we model that? So what we used is a Parker model of the wind. We've actually also used a Weber-Davis model, and it turned out that the results from those were identical for these stars. So we've decided to go with the Parker model for a simpler occasion. So in that case, what we do need is the mass and the radius of the star and its temperature. The temperature we calculate from X-rays and the mass and radius are generally measured. So that is how we determine the entire structure of the wind.
Okay, sorry. Hello, this is Leonard Barao from Leibniz AIP. Thank you very much for this great talk. Can you comment? You mentioned that you have two stars or a couple of stars for which you know the magnetic field strength are the red points in that plot. If I'm not wrong, right?
Yeah.
So those are Zeeman Doppler imaging measurements, if I understood correctly. What would happen if, I mean, Zeeman Doppler imaging misses a lot of magnetic field?
Sorry, that was breaking up a bit.
Sorry. So Zeeman Doppler imaging misses a lot of the actual field strength, right? We learned this morning. So what would happen if, let's say, the field strength would be 10 times larger in that plot?
In this okay, just to repeat the question, the measurements that we do have for the magnetic field are based on Zeeman Doppler images, and they can miss quite a lot of the field. What would happen if the magnetic field strength for these stars was instead 10 times larger than what was actually measured? So the first point here is that the magnetic field strength that matters for this measurement is very much the large scale magnetic field strength. So it's always, the dipole is going to be the most important factor here. The small scale variations on the surface would only really bias this method, because I need to know what the field looks like out to the radius where this emission was produced. And what it looks like on the surface is not always relevant. Now, if it turns out that the dipole component was in fact underestimated by a factor of 10, what that would do is roughly all of these points here, the difference between the average estimate and the maximum estimate is roughly a factor of 10 in the magnetic field strength. So if it turns out that GJ 1151, instead of having a field of 150 Gauss, had a field of 1.5 kilogauss, it would be roughly up here. And the same goes for the others. The most important thing, though, is that the dipole is the component that matters here, because I am going out to radii where the larger scale components don't really matter as much. But yes, that would push it up by roughly an order of magnitude. For GJ 1151 specifically, actually, there's been several maps that have been made, and the difference between those is also varying. So what I've done for this plot is I've taken the highest dipole strength that has been measured. If I instead take the 60 Gauss that's also been measured, that would push it down to roughly around there.
Okay, we have so many more questions, but not enough time, unfortunately. So let's thank Sanne again.